So gear teeth the teeth slide and roll for most of their contact. And the only point, like I said, where they're pure rolling is at P. But that also tells you that there's friction, and they generate heat and they lose energy. So this is where you can lose efficiency in gears. If you put a ton of gears in a row, put a motor on one end, a lot of energy will be lost from the friction of the sliding teeth in that joint, and there won't be as much power on the output. Okay, and that's because they're sliding and rolling from C to P and then from P to D, right? Okay, because if gears were truly rolling, purely rolling their entire thing, then there would theoretically be no friction or extremely low friction, and because no surface is relatively sliding if it's pure rolling, and they'd be very, very energy efficient. Okay. So anyway, that's some complexity there. The truth is they're sliding and rolling, but we model them as if they're only rolling, and they certainly only have 1 degree of freedom. Okay, right, because the teeth can't shear off from sliding. Okay, so now we're finally able to introduce the pitch circle of this set of gears. Okay, the pitch circle is the circle that goes through the pitch point, P. Okay, so if you know where the pitch point is and you know where the center of the gear is, then that green line is the pitch point. Sorry, that green line is the pitch circle. So that is what the pitch circle is. That is what you draw on a skeleton diagram. And by the way, where they do touch, that is where there's pure rolling, right? So it does make sense if you have a skeleton diagram and you show the two circles, you just draw those circles instead of drawing all the complexities of the teeth and everything, that you would say it's a J1 and it's pure rolling there. And it actually, that's the only spot where the teeth are pure rolling, okay? Okay, so the radius of that circle is R, so in this case R2 and R3, okay? And that is the critical radius you use in your analysis whenever you're comparing two gears. Now notice, if you didn't have a set of gears, there would be no pitch point, because the pitch point is basically the instant center between the two gears, and if there's no two gears, there's no instant center, there's no P, and you don't have a circle, right? So you need a set of gears to define the pitch circle, okay? Okay, so what is the base circle of each gear? Well, remember, the base circle can exist without a set of gears. It just exists. If I give you any gear and you look at its involute profile, you can back deduce its base circle. But one trick is the base circle will always be tangent to the line of action of a correctly designed gear, right? So if a gear has involute tooth profile and is obeying the fundamental law of gearing, then it has a line of action that doesn't wobble or oscillate or change according to the theta 2 input, and that line of action will be tangent to the base circle. Okay, so you can see, and where they touch here, by the way, is point A, and this is point B. Right, so if you take the radius of the base circle, the orange circle here, okay, and you find the radius line that is 90 degrees or perpendicular to this black line, where they both touch, that's B and that's A, okay? So those are going to be important. Remember, C and D are where the gears first touch and release. A and B is where the line of action touches or is tangent to the base circle. Those are going to be important later. Okay, and also notice here that for this base circle, the teeth actually go below the base circle. You see this tooth here? There's actually part of the tooth below the base circle, this orange circle here. You can know that profile that's below that circle is not involute, right? Because remember, involute contours can only exist above this circle. So starting from here on out along that curve, if you can see it, I wish I could pause it, that is the involute profile, okay? But everything below that base circle can't be involute, Okay, so that's one other little interesting insight. Okay, and they could cut this to be any shape they want. It has nothing to really do with the performance of the gear, and it's obeying the fundamental law of gearing, because below it, that whole contour below the orange circle is irrelevant. It's not. It can't be involute. Okay, so what are the addendum and dedendum circles? Well, these are the easiest circles to find. They are the circles, the blue circle. The blue circles are the addendum. They're the circle that is along the top flat of the gear teeth. And the dedendum circle is at the bottom flat, wherever you cut these teeth. That's the dedendum circle shown in purple. Now, you don't need a gear set to define those. If I just handed you a gear, you could easily identify the addendum and dedendum, okay? And so they're just the top and bottom flat circles, okay? And the pitch circle pretty much always lies between them, but remember, it's not usually halfway. It's the circle that goes to the pitch point, and the base circle can actually fluctuate. In this case, the base circle is larger than the dedendum circle, but that's not always the case, and that'll be another point here. Okay. Another really interesting point is note that points C and D lie at the intersection of each gear's addendum circle and the line of action. Okay, so what we're saying is this line of action, this black line, wherever it intersects, say this addendum circle here, will be C. See, the black line intersects this blue circle here at C. That makes sense because that's where these gears will first touch. So they'll obviously first touch right at the tip of them. The addendum, that's where they'll first make contact, and then the addendum of this circle and the black pressure line is D. That's when they'll release. Okay, and that's obvious. That's when the gear starts, and that's where the gear ends. Okay, but it's a nice insight. You want to remember the line of action where it intersects the addendum circles defines the C and the D point. Okay, so the pressure angle of a gear set is the angle between the tangent line here of the gears, okay, the line perpendicular to the line of action, okay, and the line, this line is perpendicular to the line of centers, so the horizontal tangential line to the gears, perpendicular to the line of centers, and the pressure angle is between that line and the line of action. Okay, so the pressure line, so this black line going up here. Okay, that's the pressure angle of a gear set. Now remember, you have to have a set of gears to have a pressure angle. I can't just give you a gear and say what's its pressure angle. It doesn't exist until you mesh it with another gear. Once you mesh it with another gear, it is the angle between the line of action and that horizontal line there. Okay, that's perpendicular to the line of centers. Okay, so I said that right this time. Okay, so what's the condition for two gears to mesh properly? Okay, so you can't just grab any two gears and expect to put them together and have them work. So, but what has to work for them to mesh properly? Well, they certainly don't need to have the same number of teeth. You can imagine there's lots of gears where there's tons of teeth, a large gear, large wheel on a tiny pinion. So that they don't have to have the same number of teeth, or they don't have the same sized addendum, dedendum, pitch, or base circle. They don't have to have the same size of any of the circles. In this case, since they're the same gears, they had all the same, but they certainly don't have to. And by the way, the point of these gears would just be to change a constant angular velocity into the same constant angular velocity on a different axis, which sometimes you want to do, but usually you want to speed up or speed down or decrease the speed along a different axis with the gears. So usually you want differently sized gears. Okay? So yeah, so thank heavens they don't need to have the same number of teeth or have the same circle sizes. The only thing they have to have be the same is the diametral pitch and the pressure angle. Okay? So of course they have to share the same pressure angle, but they definitely have to have the same diametral pitch, which makes sense because if you recall, the way to physically kind of interpret the diametral pitch is to think of it in terms of the circular pitch, which is pi divided by the diametral pitch, which is basically the teeth spacing. Of course, for gears to mesh, they have to have the same spacing of teeth. If a couple teeth fit between two teeth on another gear, it certainly wouldn't mesh. Okay, you need to have one tooth fit in the spot in between for the mesh to work. Okay, so they have to have the same tooth spacing, same circular pitch, and therefore the same diametral pitch. Okay? Okay, and of course they'll have the same pressure angle. So that's really it. To mesh gear teeth, they have to have the same gear teeth spacing and same pressure angle. Okay? Okay, so if R2 is the radius of the pitch circle of gear 2, and RB2 is the radius of the base circle of gear 2, okay, so remember R2 would be the pitch circle's radius, which would go from here to here, the pitch point, and RB2 is the base circle, the orange circle's radius from O2 to C, or sorry, from O2 to A. C is not the same thing. That was a bad mistake. From O2 to A is the radius of the base circle, and from O2 to P is the radius of the pitch circle. The relationship between those is RB2 divided by cosine the pressure angle equals R2. Okay, and let's derive that for you. Okay, so let's show, remember, this is a 90-degree angle, okay, between the line of action and the base circle's radius here where it touches at A. Okay, so you have a right angle there, and of course if this is the pressure angle theta, then this will be the pressure angle theta, okay, which is right here. And if that's theta, you can know that this is pi divided by 2, that's 90 degrees, minus theta is this angle. And then since this is 90 degrees, and that's 90 degrees minus theta essentially, and you know that all these angles have to add up to 180 degrees or pi, then you can prove that this also is the pressure angle theta. So that's the pressure angle, that's the pressure angle, and that's the pressure angle. Okay? And so from that you can show that if we take RB2 right here and divide it by cosine of this theta, that's this length divided by that length will cancel and you get R2. Okay, so from that simple geometry you can show that is the correct relationship. Okay, so yep, you can directly, if you know the pressure angle between two gear sets, then and you know the base circle, you can find the pitch circle radius. Okay, so here's an example that makes the point that the order of the circles, the base, the pitch, the addendum, the dedendum, those are the 4 circles of a gear that are important. The orders that they occur may be different depending on the situation. Okay, you might recall, I think the last, this last example when I showed it, it was the dedendum first, the base circle, then the pitch, then the addendum. Now let's look at these gears touching here. Here we have, again, this is a small one, this is the dedendum circle at the base of the roots here. This is the base circle from which the base circle here is the circle from which the involute profile exists. So again, below it, this is not involute. That's involute. Okay, here's the pitch circle that goes through the pitch point, and here's the addendum circle that's kind of arbitrary. You can snip those teeth off any distance really you want. So, okay. And so we have the order dedendum, base, pitch, and addendum. But now look at this bigger circle here. Okay, in this bigger circle, here's the addendum circle. Here's the pitch circle that goes through pitch. Okay, and the base circle, and here's the dedendum circle right here. That goes to the bottom flat, but the base circle is actually behind it there. So it's closer in toward the center of the circle. And that's the circle from which the involute profile is generated. So the entire thing from base flat to top flat is involute. Okay, and they could have even cut the base down, or sorry, the addendum circle in further if they really wanted to, right? So, but the point is here in this case, it goes base circle first, then dedendum, then pitch, then addendum. Okay, so don't think you can just memorize the order of the circles. They swap order depending on the scenario. You just need to know how they're defined and where they come from. Okay, and also notice the relationships between A, C, P, D, and B, essentially. They all hold true, okay? Remember, so A is the point where if you draw from O2 to the base circle that's perpendicular to the line of action, that's where that point hits. And same thing, B is right there. Okay, great. And then C is going to be where the addendum crosses the pressure line right there. That's when the teeth first touch. And then the addendum circle of this to where it crosses the line of action is D. That's where they release. P is, of course, the pitch point where the line of centers intersects the line of action or the pressure line. And that's it all holds, okay? I notice so far in all our examples, C and D lay between A and B. That's going to be a significant thing. But if you look back on all the slides, you'll find A and B are on the outside and C and D are on the inside. Okay, that means they're well-designed gears. Okay. Okay. So now, how do you design gears? What if I literally said, "Go design me a gear"? The two things I would give you is I would say, what's the distance between the two shafts that the gear, the center of the gears, and I'd say, okay, I want that to be L, and I give you, of course, the velocity ratio, omega-2 to omega-3, or omega-3 to omega-2. It doesn't matter, right? That would be what I'd care about. I'd say, remember the point of gears is on two different shafts, some distance L apart. You want to get some constant angular velocity ratio. Sometimes you want 1 if you just want to move the angular velocity to a different shaft, but usually you want it to be something different, so you step up or step down the speed. Okay, so those would be the two things I give you. Well, you can make two equations from that. That means the radius of the pitch circle of 2 plus the radius of the pitch circle of 3 is going to be L. That of course, the two pitch circles always touch, and they touch at the pitch point. So you can know that the two pitch circle radii added together is L. And remember, from our equation, we can know that omega-2 to omega-3 is R3 to R2. And remember, 2 is always switched, and 3 is always switched there. In the numerator and denominator, okay? Okay, so basically what I gave you is L and omega-2 over omega-3. Now you have two equations with two unknowns. The two unknowns is what is R2 and R3. And you could solve those and you would draw it like this. Okay, so that's R2 and that's R3. From the two things I gave you, the L and omega-2 over omega-3, you can now find those. Okay? All right. So step 2 is now specify the pitch point. Okay? And that's all obviously where those two circles touch. And then define the line of centers, which is the red line between the two centers of the circles. And then define a pressure angle with respect to the horizontal line that passes through P. Okay, so we draw this tangential line that's perpendicular to the line of centers, and we have to define a pressure angle now. Okay, and this is somewhat arbitrary. When you're designing gears, you could pick whatever pressure angle you want, but industry standard, it's usually optimal to pick somewhere between 20 and 25 degrees, and most people pick 20 degrees as just kind of a nice pressure angle. Okay, but that's up to you to pick as a gear designer, so you just specify whatever that pressure angle is. Okay, step 3 is now, once you have that, find the lines that are perpendicular to the line of action that also intersect the center of gears. Those define the radii of the base circles. Okay, so once you have the line of action, you can draw the lines that point from the center of the circle to that line of action and are perpendicular to them, and those will be the radii of the base circles. Okay, so you can find RB3 from that and RB2 from that, and you can swap it out. Now you have the base circles. Okay. Step 4 is choose a desired diametral pitch, capital P italicized, remember, and then solve for the number of teeth n on each gear and their spacing using the equation of the circular pitch p. Small p is the circular pitch, right? So remember, p equals n divided by 2r, so you can multiply 2r by p. And remember, what this step is saying is just pick kind of a random diametral pitch, okay? And by the way, it may not work at your first pass. This is kind of an iterative process, but you can just kind of pick a random one. And then you can times it by 2r3 if you're designing trying to figure out how many teeth would be on 3. And then you would take that you take pi and you divide it by this diametral pitch that you guessed, and that would tell you the tooth spacing or the circular pitch. So you would now know how many teeth from this top equation and what their spacing is, and you could space those out along the circles. Okay, and you may find at the end of the process that the P you chose is not feasible. So obviously, if the number of teeth comes out to be like 2, that's pretty tough to fit around a circle and make gear teeth work, right? So you want to guess a reasonable diametral pitch, and if it doesn't end up working, iterate essentially until you find something that does work. But once you do that, you'll know how many teeth and how much to space them. Okay, so we're getting somewhere here. Okay, and so now step 5 is use the base circle to generate the involute profiles of the n teeth spaced p apart along the pitch circle, spaced circular pitch apart along the pitch circle. Okay, so you would you have the base circle, you could take the string, wrap it around it, and bring it up to draw the involute profile, which would only exist above this orange line, and then take a string on the other side and do the other side of the gear. So there's one involute profile going up here that would be from a string there, and then you'd wrap the string on the other way and lift this up, and it would draw the other side of the involute profile, okay? So, and you do that n times for as many teeth as there are spaced by the circular pitch that you determined from your guessed and validated diametral pitch from step 4, okay? Okay, so now you're getting close there. But now you can select the addendum A and the dedendum D and use them to determine the height of each tooth. Okay. So first of all, remember, if these were say this was the base circle or something, and you drew the involute profile going up here and it looked like that, and you drew the involute profile on the other side and it looked here, and you had gear spacings, a distance, circular pitch apart. And you have all the right number of teeth. So I probably should have drawn this an orange circle. That's the base circle, and here's the teeth we draw. Right? You can see the addendum really doesn't matter. You can cut it off wherever you want. We could have cut that there. I mean, you can't go above here, obviously. Like, this doesn't make any physical sense. The teeth have to at least end at a point. Okay, you can't go above that point. But you can make the cut anywhere you really want. It could be there, it could have been lower, whatever you want. Of course, it has to be above the pitch point, but you can see it's somewhat arbitrary when you're designing the gears. You can make you can cut it wherever you want. And then also the base circle here, if you just left it like this could be the dedendum circle, the base circle and the dedendum circle. But usually, to give it some clearance, you'd want to cut something below the base circle, some shape, any shape you really want, and it would be the bottom of this that would determine the dedendum, okay, circle, right? So you can see the dedendum and addendum circle are fairly arbitrary depending on how you cut it. And you could cut as deep as you want. You could make this look like Mickey Mouse, whatever you want, cut it below the base circle, and the bottom of that would determine the dedendum circle. And you can cut it any way you want because the shape of this doesn't matter at all because it can't be involute. It's not going to help the gear fulfill the fundamental law of gearing because it's only above the base circle that it can be involute. Okay? So, but as a rule of thumb, even though I say it's kind of arbitrary how you pick the addendum A, which is, remember, from the pitch circle, say the pitch circle is going through here, the addendum is the distance from the pitch circle to the top flat, and the dedendum is from the pitch circle to the bottom flat, from there to say there, right? You could, as an industry standard, usually do 1 divided by the diametral pitch, And for D, the dedendum, you usually do 1.25 divided by the diametral pitch that you ended up choosing. Okay, that's usually a good rule of thumb if you're designing gears. Okay, so it's not just totally arbitrary. And that will usually make it so there's nice clearance and the teeth don't collide in any bad way. Okay? Okay, so that's how you do gear teeth design, or just gear design. Okay, so let's look at some gear issues here. Okay, so we're going to talk about interference, undercutting, and misalignment. Okay, so interference occurs when teeth come in contact along portions that are no longer conjugate. In other words, they no longer maintain a constant angular velocity ratio. They don't obey the fundamental law of gearing. This occurs when the teeth come in contact along portions that no longer exhibit involute profiles. Okay, so consider the example below here. Okay, so this is a tooth. This is a gear design that has something kind of messed up about it. And I'm not sure you see, but you might notice point A, which remember is basically where the base circle is tangent to the line of action here. Okay, that's A. And B is, again, where the base circle of the other gear touches the line of action. You might notice A and B lie between C and D. Okay, where C, remember, is where the gears first touch. That's where the line of action intersects the addendum. And where the line of action intersects this addendum, that's D. That's where they first release. Now, if C and D are outside A and B, okay, which is the first time we've seen this occur. If you look back, all the past examples, A and B are on the outside of C and D. But if A and B are between C and D, then when this gear first touches at C, where they first touch, it will, moving from C to A, this edge right there where it first touched at C on the addendum, okay, that will scrape down below, as the whole gear mesh moves from C to A, that will scrape down below the base circle of this tooth. And below the base circle of the tooth cannot be involute. So for the entire time of contact from this tooth to that tooth between C and A, they're touching along non-involute profiles. And as a consequence, those non-involute profiles will cause the line of action to fluctuate. The line of action won't always be normal to their interaction, their surfaces. It certainly won't be, the teeth won't always be tangent. They'll be digging into each other. The pitch point will move along the line of centers. And for just a moment, while they're moving from C to A, there will be what is called interference. And the pitch ratio, or the ratio between the pitch circle radii and the angular velocity, will fluctuate, and the fundamental law of gearing will be violated. So this is bad. This is called interference. Okay. Okay, and here's what I'm saying: recall the portion of gear teeth below the base circle are not involute. So if it first touches at C and that's outside of A, that whole time from C to A, it's going to be rubbing, and likewise from B to D. Okay. Gears will contact in that region and will thus cause interference if points A and B lie between C and D instead of the other way around, as was the case in all the previous examples. Okay? When interference occurs, the profiles of the teeth are not yet tangent to one another and thus dig into one another, and it's bad news. Okay? So for just a tiny fraction of the gear's rotation, the angular velocities will fluctuate, fundamental law of gearing collapses, and you've got issues. Okay, so that's called interference. Okay, and again, I can't stress this enough. The check is if you ever have A and B between C and D, you will have interference. Okay, if you can design the gear so A and B lie outside of C and D, you will not have interference. Okay, and you'll be happy. The gear will work great, and the velocities will never speed up or slow down for the input velocity being constant. Okay. If you have interference, there's a couple things you can do to fix it. You can do undercutting. Okay, so a possible solution to this problem is to undercut the gear so there is nothing to dig into in the region of interference below shown here. Okay, so for instance, remember this is the base circle. Okay, from which see base circle 2. That's the base circle. This dark black line. Okay, that hits, is tangent to the line of action A. So you can know that only above this is the involute profiles. Below this is not involute.